Awesome. Excited to be here and see the momentum growing with OCUDU. So I guess I'm going to talk a little bit about the AI RAN side of things, which has certainly gotten a lot of excitement recently, especially if anyone followed the GTC DC event, the events with Nokia, NVIDIA, and T-Mobile, and interest in this space has grown. But I think there's a lot of concrete, exciting things we can do here. And I think OCUDU is in an amazing place to be a platform for a lot of this work. And so I'm going to talk a little bit about kind of what is AI RAN at a high level, and then kind of what's going on with standards, and then kind of how do we see these intersecting and some of the opportunities for OCUDU in 5G and in FutureG to help host and accelerate AI RAN solutions. All right, so this is kind of the silly high-level version of kind of what's happening in everything in the world right now, but definitely RAN as well. We've been through Open RAN and virtualization of RAN. This has happened rapidly and is continuing to happen now with OCUDU being an open software platform for vRAN and ORAN. And once we turn everything into software, obviously it can be changed very quickly and adapted. And we know in 5G, every cell had something like, tens or hundreds of thousands of parameters to tune. It was a combinatorially hard problem for operators. When you start looking then inside the stack, it's this even bigger problem of millions and billions of parameters to tune to get optimal performance for everything that you could tune against. And so AI now is coming along, and, nearly everything in the stack has some decision and some modeling and some, optimal assumptions behind it. And if we now have, this whole idea of differentiable DSP software, and we have, these high level KPIs, we have data sets to tune to, and we have, very complex software, there's inevitably this massive intersection space of things that AI can help you tune better, for your deployment, for your data, for your users. And so, the natural thing here is for AI to really help optimize this software for whatever your end use is, and to think through this end-to-end optimization. So as soon as software is eating RAN, AI, I think, wants to ride along and optimize all of that software. So beyond just RAN optimization, obviously there's been a lot of discussion around things like sharing compute load. We know we always have to reserve a lot of capacity for peak performance in RAN, for full rates, for full loaded cells. And so there's often a lot of idle capacity. So there's been a lot of talk about using kind of RAN sharing type strategies to use and monetize that load when it's not fully utilized. So there's this notion of AI RAN load sharing. And then there's a lot of interest now in new enablement. So ways we can use, DSP or ML to enable entire new applications on the stack. ISAC being one of the most widely discussed topics. How can we use these radio systems we have everywhere to help kind of create this awareness of the world around the RAN, which could have all kinds of new monetization opportunities for operators beyond just connectivity. And then obviously, as we look at DoD applications, there's a whole range of things they may want to do, or that private 5G customers might want to do for all kinds of different use cases. And now that OCUDU is going to be this open platform, we can obviously highly customize it kind of end to end for any such use case. So when we talk about this kind of AI native idea of what is, AI native design of some piece of a stack, I kind of like this image that Jakob Hoyt put together, which is really looking at what do we do today? Today we have this nice signal processing chain of, encoding, mapping, modulation, synchronization, estimation, equalization, demapping, decoding. We have all of these things kind of optimized for some theoretical system model. We've come up with algorithms that do each of these things very nicely that we use today. And there's this kind of natural evolution now of, how do we go from a fully expert system to, where are there improvements on that are useful? And, the natural first thing to do is to look at each box individually and say, can I do a better job synchronizing or channel estimating or demapping, and look at replacing these specific functions with something that's maybe learned or can be tailored to things like the channel distribution or the user distribution better. And then starting to look more end to end. So like if I need to do channel estimation, equalization, and demapping, do I care about the intermediate values there? Like I may actually really just want the best, error vector magnitude in my symbols or my soft bits, however I get there. And I want to just learn an end-to-end function approximation for this. And then the end limit of this is that, the entire system is just kind of trained end to end. So I really care like maybe what the PSNR of my video that I'm watching is versus the, spectral efficiency over the channel. And in the limit, I don't care how we get there. I want ML to optimize it kind of natively and, without pre-designing all of the things in the middle. So this is kind of the extreme end of it. And there's this kind of continuum in between. So AI-RAN Alliance has kind of started up in the past 2 years here, and is obviously looking very much at these topics as well, and is now also very interested in OCUDU as a platform to potentially explore these things. And in the Alliance, they've broken it into this AI for RAN, AI and RAN, and AI on RAN, where AI for RAN is kind of all of the modem optimization, focused on improving the spectral efficiency and the energy efficiency of the RAN using ML techniques or AI techniques or really any techniques. Whereas AI and RAN is really much more focused on this RAN sharing concept of, we want to put AI everywhere for LLMs, for vision, for robotics, for all kinds of systems. Can we share infrastructure? And is there an opportunity for operators to monetize the infrastructure they already have out there to do this sharing type concept? And then there's AI on RAN, which is looking at, what are the new applications that AI can optimize on the RAN? So these are just some example use cases. I mean, right now, AI RAN has kind of exploded into like thousands of different use cases where you can potentially use AI to improve RAN performance or new opportunities for our business models or new applications. So these are just kind of some examples of different AI for and on RAN use cases. So certainly things like the receiver have always been hard to optimize and have had huge amounts of research put into them in terms of how do you fully optimize a receiver. So for things like push and SRS and Pratch, these are opportunities to improve network performance. Certainly some of the things like beam prediction, beam control, and channel prediction and scheduler algorithms are all places in the RAN stack where, there's massive bodies of research in how to improve these things over many years. And now we have, yet another very strong tool set to try to continually improve on these using data and compute. Then I guess, we've started to look further out at, at 6G and FutureG. So the study items basically started this year in June. And so we are now underway with 3GPP study items, starting to look at kind of initial decisions like, what should the modulation be? Should we consider things like constellation shaping? And there's a handful of different study items there. And so things like this AI native error interface, I think are very exciting because it's like, how can we really maximally look at learning in the stack to improve capacity and efficiency and value in the RAN? Certainly things like slicing, energy saving, this idea of a RAN digital twin to help kind of model the propagation environment and the activity around the RAN. So AI and RAN, there's been a lot of work looking at can this enable low latency deployment at the edge of inference models, of autonomous vehicle control models? And then AI on-RAN, there's, spectrum sensing, ISAC, and kind of the model management architectures. These are all kind of topics that are being looked at. So it's kind of a very high level of, there's a lot of different use cases. And so AI RAN is a very broad term, I think. So what can this look like? I think each of these has somewhere within this Open RAN stack and architecture that's kind of nicely suited for hosting it. This varies depending on the application. There's been a lot of work so far in things like RIC XApps and RApps, which have either near real time or non-real time type timing constraints on them. So they're not sitting coincident with the DU. I think when we look at AI for RAN, a huge number of these applications are combined with the L1 and the L2 functions. And so they are kind of in a more real-time context. And so OCUDU, by really opening up the DU and CU as a major platform, I think is a huge opportunity to kind of bring in a lot of these new, especially AI for RAN use cases directly coincident with the DU. And I know there's been some great work on DApp concepts recently. And I think there's a great opportunity here to figure out, how portable can these type of applications really be? We have the limit here of we can build them on top of this nice open DU architecture. But we can also look at, what are the right abstractions and what is the balance between, nice ORAN abstractions and performance critical and latency critical integration, to kind of find the right balance there. Yeah. So, right. So I think we've tried to look at, I think we're going to have to start looking at, what are the key AI RAN use cases that are going to have the biggest impact on the industry, right? So there's a huge number of potential use cases here. And I think, some of the ones we've started to look at so far are clearly looking at spectrum sensing, looking at things like RAN digital twin, where you can start to take channel response information from a network and kind of warehouse it to look at like, what is that distribution of the channel in this sector, or how does it change over time to help tune different RAN functions? Certainly there's been a lot of work looking at the neural receiver for uplink enhancement. Uplink performance is becoming super critical as different, apps transform on the phone to make it more uplink intensive. I know this is a major concern for operators. And so this is kind of a real opportunity to get out in front of these sorts of things on top of OCUDU. And certainly, I think, as we've heard alluded to this morning, I think there's a huge amount of interest in ISAC and making OCUDU kind of a reference platform for some of these sorts of techniques. I mean, really the exciting thing with OCUDU is that, we have this open platform now, which hopefully can really span the whole range from early research and prototyping through production and deployment. And I think that this range is critical for AI RAN because you can only really test a lot of AI RAN ideas in deployment or in production when you have the actual data distributions and KPIs from your network. And so being able to go all the way from research to production with this sort of a stack, I think is hugely powerful for testing and validating AI RAN concepts as they develop, and really validating what works. So some of the things that DeepSig is starting to look at in conjunction with SRS on this OCUDU effort are how can we really build out some sort of reference architectures for AI RAN for some of these key use cases that are of broad interest, so that we can have kind of pre-baked ways to do data collection, to do KPI validation, to be able to do playback and simulation, And so, you know, building on top of srsRAN and OCUDU, you know, we now have this platform that can really help do all of these things very quickly. And I think really hopefully help accelerate a whole bunch of researchers to take these ideas and try them in a production stack much more quickly. So this is really one of the goals, I think, is that accelerating this FutureG research, bringing it to somewhere where it can get put into the field and tested and vetted in over-the-air type deployments, I think is really what this field needs, because we have this gap between you know, test and deployment, and we just need to close the timeline and close the tooling to make that that process faster. So right. So then I think, you know, there's this other topic of standardization. You know, I think it's been discussed already this morning, you know, this whole idea of, can we create this network effect where we can all collaborate on FutureG ideas, try them out, have maybe interoperable software functions around them, that we can prove them out much quicker in a collaborative way than a standards body does today. And so really one of the major hopes here as well is that if we can get kind of joint interest and multiple people working behind certain reference designs and certain AI-RAN use cases, you know, we can mature these things very quickly. We can use them maybe in custom networks, but we can really build the data and the maturity and the alignment that we need to go into the standards bodies and help shape out the 6G and the 6G advanced in the future around these concepts. Because right now, you know, that pre-standards process is just the thing we need to, you know, accelerate so that we have more representation and more structure and impact there. Right. And I think, you know, in the AI-RAN area, there's also this kind of reproducibility and in comparison crisis. You know, I think having some sort of a standard set of baseline tools, data sets, integrations, you know, can really help with this, help provide kind of uniformity to how do we compare different solutions and have more interoperability in the solutions people can bring into the stack. So these are just some examples of some of the efforts we've done. And so a lot of this was developed, you know, outside the context of RAN. But I think, you know, we're extremely excited now about OCUDU as a platform to start, you know, bringing these types of capabilities onto the RAN to be easily deployed jointly. So things like spectrum sensing have been kind of widely discussed and used. And I know there's some demonstrations here also looking at spectrum sensing. But there's a huge amount of interest now around 6G and what spectrum we'll use, and will we need to refarm spectrum from other bands? Will we, you know, this is the discussion around Wi-Fi and cellular sharing in Europe right now in the 6 gigahertz band. So I think that, you know, we know there's going to be a need for more of this sharing. And if we can build out more of these sorts of mature sensing capabilities into the stack, we can really help, I think, accelerate the pre-standardization coordination in this area. So I think neural receivers are something that are getting a lot of traction now in even in 3GPP, you know, looking at what is the actual uplink enhancement in terms of sensitivity and spectral efficiency that these types of systems can achieve. So this is one of the things that you know, we've been working on for a long time, but are now really looking at, you know, how can we help bring this and bring open reference designs for this sort of approach into OCUDU. And here there's kind of two versions. There's looking at, you know, single-sided neural receivers where you're not changing the standard. You're just kind of a transparent implementation approach where you're improving uplink. And then there's this look at next generation waveforms where if you're learning how to transmit and receive jointly, you can start to look at new waveform optimization within this context. So, you know, this is something we were showing just a concept of this at NVIDIA GTC. demonstrating, in some cases, this can really provide, pretty significant throughput increases. So this is something where we've been engaged with 3GPP as well as ARAN Alliance, and I think we need to build interoperable reference designs here so that multiple vendors can try this out, can start to build, UEs that work with the infrastructure. And so we really need this kind of like an open reference design so that anything that changes the standard and has to interoperate across that interface can be easily replicated, prior to haggling over every word in the 3GPP meetings, essentially. Right. And then, ISAC, I think, this is a super exciting new use case for our radios that are sitting all over the place in the infrastructure. There's an enormous amount to optimize here. When you look at the waveform design, when you look at how you do the return radar processing, how you do the delay Doppler type mapping, how you do the target tracking and resolution, there's like a huge class of problems that AI can help you solve here. And so I think this is clearly one of the more exciting AI RAN use cases. And I think that there's a multi-domain aspect to this. So normally when we talk about ISAC, we're talking about kind of this active radar type approach where the genome B is emitting and receiving a response monostatically or bistatically to map out passive reflectors. But I think really this is a multi-domain thing. I mean, if we can combine monostatic with bistatic with channel responses within inherent network traffic reflections, as well as passive emitter detection, this is really, I think, the route to which you're going to be able to build a really comprehensive awareness engine that runs on top of the RAN. And so I think now, we really need to be able to start building out this sort of an open design to prototype this, to be able to combine all of these things, because it's really a lot for any one lab to try to, build this whole thing from scratch. All right. So RAN digital twin, I think is something that's been getting a lot of interest. Even in 3GPP, there's been some discussions around this. But the idea really is that, you have this flood of information in your network. You're constantly doing channel estimation at the UE and at the G-node B. And so you have these impulse response recordings from all of the network elements. This is an enormous amount of information. So if I can take these impulse responses and go back to calibrate either a ray tracing type model or even one of these kind of differentiable ray tracing models like a NERF or a Gaussian splat for the spatial area around the RAN, I can start to build a really, really accurate propagation environment. So this is critical if you want to optimize receiver performance, if you want to optimize things like beam layout, beam control, beam prediction, or even localization techniques. This is kind of all of the raw fuel you need to do all of that optimization. And that data is really local to the sector. So, you really want to build up these data distributions for the place that you're deploying your RAN. And so I think, starting to build out some of the tools for this sort of data extraction and model building for the twin of the RAN is going to be a really powerful enabler for helping to optimize for all of these use cases as well. And this is just one example, looking at a two-sided neural receiver, but in this case you can see between the green and the yellow line here, the only difference is you're training it on local data. So the idea is that you have a neural receiver, but if I can fine tune this for site-specific data, I can push another half a dB out of my network sensitivity. And so this sort of local tuning for site-specific models, I think is really powerful, not just in the receiver, but in many, many functions within the RAN. So where is this going in 3GPP? There's a huge amount of discussion now around kind of AI RAN use cases. A lot of these are still kind of in the study phase. But if you break down the discussions for the 3GPP RAN 1 meeting in Dallas next week into kind of the 5G advanced and then the 6G topics, some of the major items are looking at these things like CSI compression. So for helping control downlink beams, you have to send the CSI back up from the UE, and this can be high overhead. So this is one of the key areas that will be kind of adopted probably earlier than other use cases, looking at using ML techniques to compress that CSI and to fine tune the way it's encoded maybe for different sectors or different code books. And then, there's a lot of discussion around beam prediction. So how can ML models for, beam patterns and beam tracking be used to improve performance? Positioning is another big one. And then general energy efficiency optimization. So these are all kind of major topics now within the 5G advanced scope that have a huge number of documents and contributions active in this study discussion. In the 6G topic, there's been, I think I've been actually fairly impressed with the aggressiveness of some of the members in terms of exploring like the far out AI RAN use cases. So things like semantic communications, which look at joint source and channel encoding for different types of end use cases, are being considered and promoted by some members. ISAC is certainly a huge topic there. And then this two-sided AI native air interface has a fair amount of active discussion going on, as well as discussion around digital twin and different holographic MIMO type methods. So there's a pretty comprehensive list of ways AI RAN is being discussed in the standards, but all of these really need like data. They need mature prototyping. They need field measurement. Right now, the companies that can really do this themselves maturely is kind of a small group with large R&D budgets. And so I think the idea of being able to build some of these as open references on top of OCUDU could really go a long way towards helping validate these techniques and to make them work on an open platform. So finally, I mean, this is just kind of what is the focus here? So if you look at the motivations for a lot of these AIML study and topics in RAN 1, spectral efficiency, energy efficiency, and cost efficiency are kind of like the key drivers here. And, I think this message has come all the way from the operators that don't want, that really want to optimize for all of these key performance metrics. And so, a huge amount of the work is really motivated on efficiency and performance of the system, on coverage enhancement, user experience, and then some on new services. And then finally, I mean, back to the AI shark eating the world. If you look at 3GPP TDocs, you see the same thing. So, in 5G Advanced, something like 67% of the TDocs for the meeting next week are in some way using AIML within their proposals and discussion. And when you start to look at the 6G based TDocs, here it's something like 76% of them. And so it really is being woven throughout the algorithms and the thinking for almost every different feature and piece of the stack. So it's something that we definitely need to be thinking about, as we build out this open RAN software stack. Like, how do we, build this nice coherent framework that can accelerate both the interoperability and the speed of innovation and the speed of transition into production and deployment um, to go alongside this. So I'll stop there. And I guess if there's any quick questions, I'm not sure I am on time.
Yep. On the your tuning, you're talking about tuning with the additional twin, right? Which I think is fabulous, but it does produce a kind of messy. Explain the dynamic today we build systems to do specific thing. It has them thoroughly make all the United States. And so you're suggesting that the system build should adapt. But algorithmically, I get that from time. How do you know it's going to be the system? How do you address testing as well?
Yeah, so the question is about digital twin and the stability and safety of testing against these specific models, right? And I think, I mean, this is an enormous aspect to consider as we prove out the safety and resilience of different AI models, right? So like having ways to have guardrails. We've certainly seen the use of guardrails in LLMs and things. You know, you can build guardrails for RAN functions as well. You can do things like, you know, testing data sets for generalization or for, you know, different curriculums for how do you train for a specific environment while maintaining general purpose. So yeah, I don't see any of that as a, you know, these are all just problems we have to solve and validate. And we have a really nice set of ways to validate RANs, right? Like we've known how to do this forever. You know, now we're just looking at like, I can actually train and test in more specific environments. So I have to be able to cover that as well in my test. Yep.
I'll actually just kind of want your perspective on something. So yes, I understand the AI for and the AI with RAN use cases. The AI on RAN really doesn't quite resonate with me and with others I've talked to. So it's really kind of a two-part question. One, can you talk a little bit about your perspective on the AI on RAN? And the other question I have is maybe a little bit more philosophical, but it feels like the AI for RAN is a path we've already been down with kind of like the CSOM efforts we've seen in the past. So I wanted to get your perspective on that too.
Yeah. So I think for to address the AI for RAN, I mean, I think we've definitely, RAN designers forever have been working to improve spectral efficiency. And definitely SON was a whole step towards, you know, how do we explore more parameter tuning to optimize the network. I think the thing now is we can tune more parameters, right? We can parameterize all the different pieces even inside the stack. And so there's just more tuning we can do. And we have tools really good at exploring that combinatorial space now. So I see this as kind of the evolution of SON. I mean, it's now a new, more powerful kind of a SON that can explore, you know, even how the receiver should function. You know, even the direct algorithms for some of the processing can be tuned rather than just tuning like tilts and power levels. And you know, we've just gone kind of to, you know, a much more in-depth version of SON. And then for AI on RAN, I mean, I think certainly things like spectrum sensing and ISAC. If you think about DoD use cases, they care a lot about what's going on in the spectrum. You know, things like drones have gotten enormous interest and have an enormous need for this broad detection. And these aren't directly contributing to the RAN communications function, but they're using the RAN as a platform to enable these new types of sensing. So, I mean, that's kind of where I see AI on RAN is you're really enabling new applications that the RAN can deliver that aren't necessarily the connectivity that it was built for.
All right. It makes so I have an OCUDU reasons. So, you know, this NVIDIA Nokia, right, effect, I like to call it NVIDIA Nokia effect, right? They kind of hijacked the AI RAN movement, right? And they're trying to pitch it as this, you know, cellular Akamai kind of a company that we basically produce mini data sectors everywhere, right? And then you can sell probably to the applications and make more money. And that sort of this AI all-RAN or AI 4RAN, they kind of podcast. And ORAN was kind of pushing AI 4RAN thoughtfully. So my question is, do you think this Nokia NVIDIA effect will have a positive impact to the ORAN adoption or a negative effect for them? And why would you, how you justify it?
Yeah. So I think it's hard to read the tea leaves on exactly what the impact will be here. I tend to be optimistic about it. I think that NVIDIA is maybe trying to open up the adoption of some new technologies into the Nokia RAN, and try to open up that ecosystem a little bit more, to bring in new innovation. And I think it's brought a huge amount of new interest and validation towards this entire ecosystem. And it's excited a number of new operators as well around the world that are really starting to look at, how can we go and start to deploy AI RAN. So I think NVIDIA is working with many sides of this equation, open and not. And I tend to think this is a really good thing for the whole ecosystem, and that it's going to accelerate the pace of AI RAN adoption and carrier interest in deploying and vetting these technologies much sooner. So I think it's a really good thing. And I was excited also to see this aerial and FlexRAN, FAPI integration for OCUDU, which I think is very powerful too, and having a stack that can be tested with other components like this. So. All right. Thank you.